Hello, everybody. I want to welcome you today to the CMI webinar series designed for and by CMI. And I'm Cynthia Howell, and with the Education, Training, and Outreach for CMI, and I will be your moderator for today. I want to tell you a little bit about this webinar. First, CMI webinars are hosted by Colorado School of Mines, and we kind of broadcast from all over. If you have a suggestion for a webinar, we'd love to hear that. And please email that at cmi@mines.edu. This is a public webinar, and a recording is going to be available next week at aimslab.gov/CMI. And it will be under the webinar menu. And do note that we also have a YouTube and a Critical Materials Institute channel options as well. Questions. We are going to hold questions till the end of the presentation. However, we will take your questions immediately. So please put any question that you have that you're pondering as soon as you have it, so it won't be lost by the time we get to the end. But again, those will be finished at the end and answered at the end of the presentation. I want to take a little bit of time now to introduce our presenters, and we'll have one presenter and then two others joining in on the question and answer. And for today, we have Jeff Whalen. He's the Director of Magnetics Corporation and the STEM Entrepreneur in Residence program at Florida State University. Also, he holds a PhD in inorganic chemistry from Florida State and was a postdoc at the National High Magnetic Field Laboratory. He's been quite an entrepreneur and has started multiple companies, and which adds to, again, great experience that he's bringing into this particular program that we're going to hear about today. Jane Wadhams is a scientific research specialist and an analytical geochemist at the National High Magnetic Field Laboratory. And she's spent the last several years working on track elemental migration in the Florida phosphogypsum waste streams, and has been instrumental in the Gypstack research project that you're going to hear about. And last but not least is Lezlee Richerson, this Chief of Staff at the National High Magnetic Field Laboratory, with 20 years of experience working in all kinds of research administration and projects at Florida State University, and also at the National High Magnetic Field Laboratory. And she's been instrumental in bringing the funding together for this Gypstack project. So I don't want to take any more of your time. Jeff, if you want to take over from here, we'd love to hear from you.
That's great. Thank you so much. Appreciate the introduction. And you all should be able to see my slides now. And per the introduction, my name is Jeff Whalen. I am a chemist by trade, but honestly have found my way into many other forms of research, engineering and physics. And I'm a Florida native, grew up down in South Florida and moved to Tallahassee in 2001. I joined the team at the MAGLAB in 2009 and worked here for about 10 years before moving over to main campus to teach STEM entrepreneurship, and more recently came back to direct the project that I'll share with you today. A little bit about the MAGLAB for the general audience to give a sense for who we are and what we do. We are kind of a unique facility in the perspective of all of the other national labs in the United States. We are perhaps the only one, if not one of maybe just a couple, that are not primarily funded by the Department of Energy or the Department of Defense. Our primary funding comes from the National Science Foundation. And the call to the mission of the MAGLAB has been to operate a world-class user facility program that I'll share a little bit about in a moment. But really the sort of claim to fame and what gets talked about the most out there in the real world is that the MAGLAB is home to the most powerful magnets in the world, literally the most powerful magnet in the world that's still operational today and made available to the scientific community through that user program. Pretty much in any way that you measure the MAGLAB here in Tallahassee, Florida, you will find that it is the premier facility for magnet technology development and magnet science research. both in terms of the giant magnets that are here, but also in terms of the number of magnet science experts that are under this roof. Some of the magnets that are here, as you can see on the slide, are 2 million times stronger than Earth's magnetic field. And the research environment that's here is really focused on foundational discoveries. So the magnet program that's operated here is made available to the scientific community on a proposal-based competitive process, but carries no fees. The research that's done on the magnets through the user program must be published. But to anybody that's on this webinar, if you have exciting or interesting experiments that you think would be benefited or enabled by very large magnet systems, you're definitely encouraged to submit a proposal through the MAGLAB website. We invite and host usually each year in excess of 2,000 scientists at the MAGLAB, and they come from all areas of the United States. Most of them are from academic institutions, but also other government labs and some industrial users as well. So really a lot of movement constantly in the lab, and everything focused around leveraging these incredible assets that are a whole host of specialized magnet systems, each one sort of developed for a different type of experiment and use case. So the mission of the MAGLAB is to operate that user program. The MAGLAB came to Tallahassee, Florida, and is hosted by Florida State University in 1990. And from then up until today, that mission has been the same, the focus really being on that user program. But the MAGLAB is also a full spectrum research facility, and there's all types of principal investigator research being led here, everything from materials to biological research and even energy and other fields. So really, it's a full spectrum research facility, just very, very focused on operation of the user program. There are also, facilities for development and construction of new magnet systems and scientific instrumentation to support those systems. So because these magnets are sort of research grade one-off systems, most of them are fully designed and constructed here in this facility, with only some of the components being subcontracted for machining or supply. So each one of these is kind of a custom magnet system and built here in-house. And then the MAGLAB also focuses on education and outreach activities. Every year, in February, there's a MAGLAB open house to anybody that's nearby Tallahassee, Florida. This is something that you can come to free of charge and come inside the facility and see what's going on. The MAGLAB here in Tallahassee is the headquarters of the MAGLAB, but there are also two sister facilities. One of them is located at the University of Florida in Gainesville, Florida, and that is the high BT facility, meaning high fields at low temperatures. And then the pulsed magnet facility is located at Los Alamos National Lab. So just an aerial shot here of what the facility looks like. It's been added onto many times. It's oftentimes joked that it's kind of a maze inside the facility, but it's a 370,000 square foot facility. It's in the Innovation Park that's on Florida State University campus. And the 4 user facilities are comprised of these 4 listed on the slide. The DC user facility, which are continuous fields, static fields up to 45 Tesla. There's a resonant user facility where continuous and pulse magnetic resonance techniques can be employed. There's a nuclear magnetic resonance facility with a large bore NMR MRI system that is the 21.1 Tesla 900 megahertz magnet, largest MRI in the world. And there is the ion cyclotron resonance facility, which has the several magnets that can be used for FTICR experimentation. There's also 2 sister facilities located on the same campus. There's the Magnet Science and Technology Division, as well as the Applied Superconductivity Center, which are just a stone's throw away from the actual MAGLAB itself. Okay, so with a little bit of background to the topic of the project that we'd like to share about today. This project is focused on rare earth elements specifically. I realize there are more than just rare earths listed as critical materials, but the rare earths are very, very important for certain types of applications and industries that have projected demand that will be much larger than we've seen at any point in history. And part of what's driving that increased demand are the global renewable energies markets, specifically wind power, which has a very high demand for rare earths in the form of permanent magnets for the wind turbine generators, as well as the mobility, which, this is electric vehicles. And, my particular favorite, that Ford F-150 Lightning in the bottom right of the slide. U.S. defense is also a large consumer of rare earth elements, and the F-35 is a great example where this next generation fighter jet is fully enabled to do what it can do in terms of vertical takeoff by an engine that can be rotated. And the articulation and the rotation of that engine is achieved by very large permanent magnets. So it's very important that those materials are present for this particular defense application. And with all of that increasing the amount of rare earth demand that's projected, and even the amount of rare earth demand that's present today, it brings us to a resource in Florida, call it a resource, maybe even not viewed that way by the public right now, that are the phosphogypsum stacks. And Florida is one of the largest producers in the world of phosphate for commercial agricultural fertilizer. So the industry itself supports a very large amount of the supply of that phosphate, and it's produced in Florida because of very large natural deposits of phosphorite that are found primarily in the middle of the state. And companies like Mosaic have been active in this industry for a very long time, but what it has produced in the process of this mining activity are what we refer to as the gypstacks. That's sort of a shorthand terminology for what is a phosphogypsum stack. Stack meaning, mountain, because in the scape of Florida, which really is a very flat state, meaning we don't have a lot of hills, especially down in the middle of the state. These are mountains. They tower over the rest of the landscape because in order to get the phosphorite out of the ground, it requires quite a bit of strip mining. And the tailings from those mines are built up in these stacks, oftentimes, as you can see, with large retention ponds at the top of the stacks. Some of the stacks are smaller by comparison, but that's still pretty large in terms of the landscape in Florida, where smaller stacks may be around 80 acres in footprint and 100 feet in elevation, and other larger stacks can be in excess of 300 acres and over 150 feet of elevation. So this is sort of the topic of discussion. There's a large and increasing demand for rare earths, and there are resources in the state of Florida that potentially could help meet that demand in the form of these gypstacks. So this demand is something that we can really start to kind of project. And I feel like maybe, at this Critical Materials Institute and during this webinar, this isn't something that I really need to sell very much. I think especially as shown on the slide here, beyond just rare earth elements, many other critical materials are going to experience very rapid increases in demand. This one statistic here for rare earths, is an increase by a factor of 7 just by 2040. So how can we position the United States to meet these demands? We know this increases in demands are coming, and we simply cannot continue to produce at the levels that we're producing now if we anticipate to meet those demands. So there's one prong in terms of meeting the demand, but there's also a second prong in terms of trying to meet that demand in ways that are environmentally sustainable and also ethical. So a little bit of history and shown through a simple plot here. This is sort of where rare earths have historically come from. And you can see that starting around the mid 1960s, the United States was relatively active in contributing to the world's rare earth supply through the Mountain Pass mine in California. And this mine was producing rare earths from ore deposits and through almost the year 2000, supplying a significant amount of the world's rare earths. But around the year 2000, the Chinese began mining rare earths and completely took over. You can see that US production went completely to zero between 2000 and 2010 until it was realized that this was laying the landscape for a challenge that could pose a threat to the United States supply of rare earths. And now, if even with the increase in the supply in the production of rare earths out of the United States, China still controls that supply chain, including 80% of the rare earths. And on top of that 80%, even the rare earths that are coming out of the United States and other countries like Australia, China is doing 96 of the world's rare earth refinement. So trying to shift these supply chains, again, in a way that can meet demand and in a way that can do so that is environmentally and ethically sustainable is our goal. So it brings us back to the gypstacks. And in the top left image here, you can see a map of Central Florida. That is Tampa Bay on the left side of the image. And each of the red dots on this map represents one of the gypstacks. So you can see there's one gypstack down on the south side of Tampa Bay. There's a couple that are further up north. And then most of them are concentrated in this central area of the state where there's not a lot of residential population. This is an area that's mostly used for agriculture. So creation of these very, very large stacks is more feasible than it is in more densely populated areas. But most of these stacks have been built in this flatter region of Florida. The construction of a stack is pretty similar no matter where you are in Florida and which of these stacks you're looking at. In the bottom left image, you can see the Riverview stack, which is one of the gypstacks that's located on the north side of Tampa Bay. And the gypstacks are produced in the same fashion, where as the phosphorite is processed and the phosphogypsum is created through that process, it is piped as a slurry over to a stack, and then the stack is built up as the slurry dries out. So as the stack is built, it creates levees, and when the levees start to grow upward by additional phosphogypsum being added, there are ponds that are formed in the middle. The ponds are formed by the rainfall in Florida, which is significant, and the water must be managed because the phosphogypsum that's produced is radioactive and contains other nutrients and materials that can't just be sent into the aquifer or allowed on the normal watershed into the marine water bodies that are nearby. So the water has to be contained on the top of these stacks. So quite literally what this is a very large mountain on a flat landscape with a giant lake at the top. The lakes are often lined with HPDE liner, basically pool liner, to keep that water from seeping through the phosphogypsum and down into the aquifer. And all of this has to be constantly managed in order to maintain stability of the stack. Instability of the stack can result in really bad things where water is discharged or the phosphogypsum runs as a slurry into areas where it's not desired to be. But it's not all bad. In these stacks are three primary co-products that could be leveraged to produce revenue. The first is the phosphogypsum itself, which really the only difference between phosphogypsum and naturally occurring gypsum is the way in which it was formed. So phosphogypsum is normal gypsum. It was just produced by a man-made synthetic process, but it has the same values. So in terms of all of the gypstacks in the state of Florida, we're looking at about 1 billion tons of gypsum that has a value of around $9 billion. Most of the time, gypsum is used in the construction industry for production of road base and drywall and other construction materials, as well as soil amendment. The rare earths themselves, it's estimated that there's about 500,000 tons present in all of the gypstacks together, which represents about $20 billion of potential revenue for permanent magnets, electric motors, and some of the other applications that I mentioned early on. And thirdly is radium and other forms of radioactive elements. About 40 kilograms is estimated in the stacks, but this represents about $1 billion of potential revenue. And most of these are used for targeted cancer treatments and alpha radiotherapy treatments. A lot of that type of research is being focused at our partners in Oak Ridge National Lab. So that gives a little bit of context of why we're looking particularly at the stacks as a potential source of not only rare earths, but also other co-products in the form of the phosphogypsum itself and the radium that can be extracted. So a little bit of a background there. We call this project the FSU Rare Earth Initiative Project. A lot of us lovingly refer to it as the Gypstack Project. And we have some very specific goals in this project that I'll share with you. The first goal is to provide a long-term solution to phosphate waste accumulation. It's probably not surprising, based on what I told you on the previous slide, that the public perception of phosphate mining in Florida and the production of these gypstacks has a very negative connotation. People don't want to see this. They understand the risks associated with unstable stacks. So how can we provide this long-term solution so that we don't continue to produce phosphogypsum stacks in the state? The second is creating new resource streams. So these are the revenue streams that were mentioned on the previous slide. So it's sort of one of these golden opportunities for a scientist entrepreneur to say, here is a business opportunity, here's a business case combined with the use of something that would otherwise be hazardous or garbage. So creating those new resource streams is the second goal. The third goal is attracting new industries based on rare earths. One of the primary goals of the state of Florida as a whole has been to focus on the production of rare earth and harden the supply chains of rare earths to be able to feed into the high-tech sectors that are reliant upon those. Permanent magnets is certainly one of them, but also things like superconducting magnets and electric motors. And then finally, for development of novel rare earth separation techniques. So, it's one thing to be able to remove all of the rare earths from a gypstack. That's great, but being able to separate those rare earths into their individual elements is also a goal of this project. So this slide in particular, I think, as a scientist, but even as a business person, is very interesting because what you're looking at is a chart that compares each of the rare earths in terms of their concentrations as a weight percent, comparing what comes out of places like Mountain Pass and the Chinese mines with what comes out of the Florida gypstacks. So in gold are the Mountain Pass concentrations, and in blue are the phosphogypsum stack concentrations. And what you can see right out of the gate is that they're very, very different. But aside from the differences where you have appreciable amounts of an element, such as the case for lanthanum and cerium, look at the cases for things like dysprosium and yttrium, where the presence of those rare earths is almost zero in the ore deposits at Mountain Pass, but there are measurable amounts of these elements found in the gypstacks. And for the case of electric motors, which perhaps is where nearly all of the upcoming demand for rare earths will come from in the near future, we have all three of these elements present in the gypstacks: praseodymium, neodymium, and dysprosium, but particularly dysprosium being so important for the production of commercial grade neodymium-based magnets due to the fact that it gives a much higher heat tolerance to the magnets. It increases the critical temperature of these magnets. So a neodymium-ion boride magnet is really crippled for most applications where the heat is any appreciable amount without the addition of the dysprosium. So really, if you were to say all of these rare earths are critical materials, dysprosium in particular out of the phosphogypsum stacks in Florida poses an incredible business case because of the high concentration compared to the mineral ores found in Mountain Pass and in China. And then also the case for yttrium. I realize yttrium is not a rare earth, but for those of you that may be chemists in the audience, you know what I mean by it acts like a rare earth. And the applications for yttrium are primarily in lasers for yttrium aluminum garnet lasers. So this incredible weight percent present of yttrium in the gypstacks also poses a very compelling business case for developing solutions for removal of these materials from the phosphogypsum and separation of these materials into their individual elements. So a little comparison. Finally, here is a flow chart. And there are processes here that are still in development and can't speak in too much specificity to some of the boxes on this process flow chart. But basically, this is showing how you start with either an ore deposit or a phosphogypsum stack and try to move through different steps to be able to have the raw refined elements themselves. And what's happening already in Florida at the gypstacks are those first 4 steps on the left of this flow chart, where getting to the point where we can calcine rare earth oxides as mixtures is already proven. It's already possible. But part of this project, as I mentioned, is focused on novel separation processes. So this colored box is significant in the fact that it's competition for existing solvent separation processes. And these solvent separation processes have been developed over a very long time. So operation of these processes is nothing new to the industry, but it is a critical step in separating out these rare earths that all have very, very similar ionic radii and properties. So what that means to everybody out there, scientist or not, is that it's hard. It's difficult to get a mixture of rare earths separated into all of their individual elements as pure elements, pure metals. So this solvent extraction process involves usually almost 1,000 steps to try to get to these individual elements. And it's very tedious. And it also involves the use of some very nasty solvents, some materials and some liquids that are not only difficult to source, but they're extremely difficult to handle and perhaps even more so difficult to dispose of when it's done. So doing solvent extraction processes is something that oftentimes is only conducted in China. There are new installments in the United States that are on the forefront, but nonetheless, this is a key step where our project here at the MAGLAB is seeking to develop alternative processes that don't involve the use of the same materials and also can be done much faster and more efficiently. Really, as the director on this project, I've always seen this as the grand slam. Being able to clean up the gypsum and make it not be radioactive and pull out the rare earths to produce those 3 co-product revenue streams, that's a home run already. But being able to separate the rare earths into individual elements is really a grand slam in terms of project success. So we've got a very dynamic landscape in Florida in terms of what people really want to see as success out of this project. Some people view this project success as getting those rare earths out, whether they're a mixture or individual elements or not. And others see this project as monetization of those 3 different co-products. And yet a third group of stakeholders see project success as elimination of the gypstacks. Me personally, I've always seen a 4th version of success that can really be mixed with the other 3, which is being able to support this very important industry in the state of Florida, because without phosphate for commercial agricultural fertilizer, we cripple the agricultural industries in our country and in the world in general. And beyond just food production, corn and soybean production for things like fuel supply and other applications are just really as important. So hopefully that gives a good sort of overview of this project and the angle in which we were coming from and the reasons in which we are doing for which we are doing these activities. And if I were to give sort of a high level synopsis of this project in terms of the science and the development, what I would suggest to take away from this presentation is that this is a relatively young project that was started only recently, and early successes in this project have been very promising. But all in all, what we are comprised of as a relatively large team of scientists and engineers are all people that are very used to the discipline and rigor in terms of drawing conclusions about innovation and new processes that are developed. So more time is needed for this project to mature and activities to continue before we are able to sort of say we've hit that home run or that grand slam, or that we're not able to. But we are encouraged by the early results in this project, and we're looking forward to what's around the corner. So with that, I will conclude this presentation, and I appreciate the opportunity to present on this webinar. And my partners, Lezlee and Jane, are here with me, and we are happy to answer any questions that you might have. Thank you.
Jeff, thank you so much for a great presentation. And I could hear the minds working over the waves here as CMI folks get an idea of what you're doing at the MAGLAB and how it relates to everything that we work on at CMI, and potentially I know there'll be some ideas of where that can connect. Thank you for the information about Gypstacks. That was probably new to many of us, and solution for phosphate waste is not new to us. We have had some researchers working on that in Florida as well. Creating new resource streams, that is amazing. Tracking new industries, or potentially having new industries as relating to rare earths, and developing separation techniques, again, right up CMI's alley. So we really applaud what you're doing, and I'm hoping that we have some great questions ready for you here. Let's see, everybody that's out there, let's start asking questions. Here we go. Will you pull up your question and answer? You'll see one from David Reed at the top.
Sure. Cynthia, should I read this question?
Please read the question so it can be recorded. Thank you.
Happy to do so. So David's question is, how accepting is the phosphate industry of the work that we are pursuing? And David, it's a great question, because I get asked a lot about the landscape of stakeholders and beneficiaries for this project. As you can imagine, it's not just sort of one party that has an interest in what we're doing at the state level, at the federal level, different stakeholders, different interests that they have. And one of those stakeholders that's a key player are the phosphate industrial leaders, the phosphate mining industrial leaders. And really, what we've been very happy to find out is that they see this in a very similar manner in which we do, as an opportunity to diversify revenue streams. And we're really excited to be partnering with the leaders in this industry, because success in our project of eliminating those gypstacks and success in the eyes of the state of Florida for remediating what is a liability right now also is viewed by the industrial players as the opportunity to create new revenue from co-products. So there's a lot of really good alignment there in terms of the industry and the project. So most of it has been very well received, and we're really looking forward to continuing those relationships.
Next question from Michael.
Thank you, Cynthia. Michael's question is, can you talk a bit more about your separation techniques in the high mag fields? Also, what applied fields are being explored? So this is an area where, excuse me, A lot more development is needed, and there's a limited amount of information that I can share. But what I can share is that we are focused, as I mentioned earlier, on replicating the outcomes of the solvent extraction processes. So we don't want to end up with something that can't compete with sort of the status quo and the way that it's being done right now. And so at sort of the highest level, we need something that can be both feasible from an innovation perspective, which is very much so an aspect that we are still working on and have not solved, but also viable from a commercial perspective. So just having a separation process work, but suffer from inadequacies or inefficiencies that make it, economically comparable to solvent extraction, still isn't that win. We really need something that's going to be able to replicate the quality of the output, but be done so at a better economy of scale. So in terms of the fields that are being explored, I mean, really everything is on the table. That's one of the incredible things about this project being housed here at the MAGLAB, is that, we don't just have access to commercially available magnetic field strengths. We can build what we need. And that's been really exciting to explore opportunities that high fields may enable, or things that we could do at low fields. But I guess, sort of in the blood and the spirit and the heart of the MAGLAB, everything is going to revolve around enablement by magnetic fields. So can't really answer either of the questions totally specifically for you, but it's a very common question that we get. And I will sort of draw back to the stakeholder landscape and say that we have so many people that we have to try to keep their interests aligned and make sure that we're serving their needs, that at the early stage in the project, we have to be sensitive to some of the information that we share.
Another question here from Jackie.
Thank you, Cynthia. Jackie's question is, are there more rare earth elements in dirt than phosphogypsum? This is another question that we very frequently get. And it's a really interesting dynamic, because I could go outside of the MAGLAB right now and take a shovel and take a scoop of dirt out of the ground, and there would be rare earth in it. There's rare earth all around us, in the dirt, in the soil, in the rocks that surround us in nature. And the concentrations that are found there aren't really a whole lot different than what we see so far in the phosphogypsum. But what is extremely different is the availability of those rare earths. And this is one of the really exciting components to the project, where we have been developing processes that take advantage of that. The fact that the rare earths are not found in their natural forms, but instead they are found in these synthetic environments that were created through the processing of the phosphorite to produce the phosphogypsum as a waste stream, and the phosphate as the fertilizer product, has made them in a less common state that wouldn't be normally found in nature. So although the concentrations aren't significantly higher that would make something like an ore deposit very attractive, what they are is significantly more accessible. So this is an area of the project that we really want to leverage.
Another question from Bo.
Thank you, Cynthia. Bo, you gave us a nice long question. All right, here we go. Do you anticipate focusing on processing the slurry before it reaches the stack, or mining the stack itself? And if mining the stacks, will you have to pump all the water from the ponds to prevent contamination beyond what is required under current conditions? So this is a very, very common discussion that we have in this project. And really what you can visualize in terms of everything that I shared in the presentation and how that's applied in the real world, there's two markets. Call them markets in quotations here. There's two applications. One of them are the existing stacks themselves. The other, as you mentioned, is the slurry that comes out of the processing facilities. And on one hand, The stacks themselves, many of them are extremely old. They've been there for a very long time. Some of them are fully grassed over by now. They're not even white, showing the gypsum anymore. And those stacks are just sitting there. There's no throughput that has to be kept up with. We're not slowing anybody down if we develop a very slow process that takes a long time. And those stacks are oftentimes reasonably far removed from the processing plants. So we've got a lot more room around the stacks to work with. And that's sort of like legacy deposits of phosphogypsum and the radioactivity and the rare earths that are contained within. So there's a whole host of possibilities for solutions on existing stacks. And then when you talk about slurry coming out of processing plants, now everything that I just mentioned does become a factor. We absolutely can't slow down the processing plants. We're going to be in dense infrastructure for the plant itself. We've got the piping that needs to come out of the plants to go to whatever processing facility is there. And then what would happen after that slurry was processed? I mean, optimally, we wouldn't want to take it and start making another stack out of it. So where would it actually go? We'd have to have those supply chains and those logistics in place to be able to get rid of this gypsum once it's had the radioactivity removed and the rare earths removed. So it's really kind of like two very different markets that need to be served, possibly by two different solutions, hopefully enabled by the same core technology. With regards to the water, though, absolutely the water must be managed. There is no question about it that to get the water to a level where it could be discharged into marine natural water bodies or freshwater natural water bodies, or used for irrigation purposes, or used for other process water, it must be managed. So that is a little bit of a secondary problem that's needing to be solved in this project, but there are a host of other projects out there that are solely focused on the water. Our main focus has been on the phosphogypsum itself and removal of the radioactivity and the rare earths.
Another question queued up from Nicholas.
Thank you, Cynthia. Nicholas's question is stating, this is more of a question regarding your novel separation using magnetics, but could there be a potential to apply what is learned in separating rare earths to native metals and alloys? That's a great question. I don't think I've ever gotten that question to date. Possibly. I think that it could be explored with a lot more confidence once those separation techniques have been fully developed. But if I were to sort of take my scientist hat off and just strictly have my business hat on, I would really be much more attracted to the case of separation of rare earths because of the commercial opportunity that they present, not only just because of the current value of the rare earths, but also because of two other factors that are poised to increase the value of those rare earths over the near term. The first one being, as I mentioned, the supply chain considerations and the fact that most of these materials are being produced or refined in China, but also along with that, the increased demand from the applications that I mentioned early on, like sustainable energy and e-mobility. So it's possible. I think we'll probably look into that once we have solved the primary problems that we're looking at in this project. But again, from a business case and also from a sustainment of the phosphate mining industry and sustainment of the environment in Florida, I think that the rare earths themselves and the gypstacks really provide the most attractive commercial opportunity.
Well, thank you for all the great questions. So you just finished answering 5 exceptional questions here, Jeff, and I'm wondering if you, Lezlee, or Jane might have a few closing comments. And in that time, if somebody has another quick question, we could also answer that. So any additional closing comments from your team?
Jane, Lezlee, do either of you want to say hi or provide some feedback?
I just want to say thanks for the questions. Those were great. Yeah, they really were. We typically don't go and do the dog and pony show here. So this is our first group to kind of talk to, and this was great questions, great feedback.
And I guess for me, closing comment would be that the last slide that's displayed here has my contact information. Please feel free to reach out to me, especially if I wasn't able to answer any questions in enough specificity, or if you have questions that you think about after the fact. We're really excited about this project and open to partnerships and collaborations, especially with the CMI community. So please take me up on an open invitation offline outside of the webinar to reach out to me by the email that I provided on this slide. And again, thank you so much for the opportunity to join today and present.
Want to thank all of you again for being here and for the presentation, Jeff and Lezlee and Jane as support. This was really exceptional, and I guarantee you will have some people reaching out to you. That just seems to be our great webinar audience that we have. So what I'd like to do right now is just thank everybody for being here today. I want to remind you that this recording will be available next week at aimslab.gov/CMI. And also you can find this on YouTube as well as the Critical Materials Institute channel. The next webinar is on April 12th with the Department of Commerce on International Trade Administration, Industry and Analysis Office of Critical Materials and Metals. So it's going to be an overview. And of course, as usual, it can be found in the Critical Times newsletter, on website, and in Ames National Lab social media as well. We're always looking for more requests for webinar topics. Again, this is for you, for all of our CMI family. And so whatever you want to learn a little bit more about, please share it with us on the survey or email us at cmi@mines.edu. Thank you again for all being here, and we'll look forward to seeing you next month in our next upcoming webinar.
Thank you so much.